Hey everyone, another day, another DSA concept. So today we're going to be looking at union find, or in other words, disjoint set union. So yeah, I'll talk about a little bit about union find, when we're supposed to use it, why to use it instead of DFS, and the time complexity, and then we'll walk through an example. So yeah, let's go ahead. So union find is basically a data structure, and it's a method which is used to efficiently find connected groups and to also check if two nodes belong to the same group. Okay, so the intuition would be if we, let's say, have four friends, right? And right now we have four friends. So we have four different components over here, four different groups. They're all individually their own group. But let's say we form a connection between 1 and 2, and then we form a connection between 2 and 3. So after we do that, we see that we're now left with two groups, right? So this is one group that they have formed, and 4 is alone in a separate group. So when it comes to union find as an implementation, there are basically two different functions that happen in it, two different operations. So one is find and the other one is union. So what happens in find is that it returns the ultimate parent or the ultimate root of a node. Okay, so if we have to look at that in the analogy of the friends group, so it's used to answer who is the head of this group, or which group does this particular individual node belong to. So that's what find does. And so it takes an input X, which is the node, and then it tells us who is the group leader for the group that X belongs to. And union basically takes two different nodes that are connected, and then it connects two groups together. So that sounds a little confusing right now. So they already have a common edge, but they don't have a common group leader. So they're connected in some way, but their group leader is not the same. So that's when you could say you're going to use a union to combine them to form one amalgamation of the group. So this is used when an edge already connects two nodes. Okay, so let's see why exactly union find works. So if two nodes with the connecting edge have the same, I've made a spelling mistake, if they have the same ultimate parent, then it means that they're already connected. So if I do a union and I send in two nodes that already have the same parent, let's say like I had 1 over here and then 2 and then 3, they both have the ultimate parent of 1. So if I send 2 and 3, if there was an edge between 2 and 3, and I send that for union, then my union find would basically return a false. And what false means is that there is no need to combine what is already combined. Okay, so now there's another condition that if two nodes with the connected edge have different ultimate parents and they need to be combined into the same group. So maybe I can give an example like this. Let's say 1 and 2, and then there was a 3 and 4. So the ultimate parent of 4 is actually 3 here. So if I combine 2 and 4, the group leader for the group 2 is in was 1, and the group leader for the group 4 was 3. So now adding this edge, I want to make a union of them. So let's say that 1 becomes the ultimate group leader, the ultimate parent of everything. So in this case, if I send this edge and these two nodes, then union find will return a true because it says, yes, we can combine them together. Yeah, that's basically the two main operations in it. And then, so there's a concept called path compression. And path compression happens in the function of find, where we're finding the ultimate parent. So what happens here is basically while finding the root for one node, we make every node point directly to that root. So we're buying ourselves time for future operations. So before, if it was like 1 connects to 2, 2 connects to 3, and 3 connects to 4. So while finding the ultimate parent of, let's say, a specific node 4, I will map, let's say all of these are connecting to 4. So 4 is the ultimate parent here. So while finding the path to the ultimate parent of 1, I'll map that all of their ultimate parents is 4. So yeah, basically, so we are compressing the number of steps by actually doing kind of like a recursive call within the function to ultimately find the ultimate parent. So yeah, if this makes sense. Yeah, so this is the way that this whole union find actually becomes super fast by this methodology of path compression. And let's talk about the 2 types of union find. We have union by rank, and then we have union by size. So union by rank is going to have a specific list, which is going to have the rank of each node. So it stores approximately what the height of that tree is. So what happens in union by rank is when we have 2 different components, we're going to, not 2 different components, when we have 2 different parts, let's say, which have different ultimate parents and they have to be clubbed together. So we're going to attach the one with the shorter height. So the shorter height tree will come under the tree which is taller by height. So this basically keeps the tree shallow. And when we want to use this is if you only care about connectivity to see if like 2 nodes are connected or they're part of the same group, if you want to check for cycle detection, or just standard DSU operations, or like if you're just given a problem and you know this, it's union find, union by rank is normally the first approach to go to unless stated or told otherwise that you need to consider the size. So union by size, it stores the number of nodes that each component has. So what you do in this case is you're going to attach the smaller node count tree to the larger node count tree, right? So you're basically going to try to keep the tree balanced by doing this. So when you're supposed to use it is if size of the connected component matters, and if you're asked a question like find the largest group, the larger area, or stuff like that. So yeah, so if it could also be in a problem where a number of nodes in each island, something like that. There are a few problems which we'll be solving after this. So I think it'll be clear when we use that there at that time. So yeah, let's check the time complexity, right? So because of path compression, it becomes super fast. So this is actually like alpha times n over here. I don't know, I think it's called alpha. In this particular problem, it might be called something else. But yeah, this, yeah, I'm gonna call it alpha. So yeah, let's say it's alpha times n. And because of path compression, this over here is basically, it makes this whole factor like a constant. So it's near constant time, not exactly, but very close to it. So compared to like a DFS, this is a very fast option. So I could just probably say it's like O of n, the number of nodes itself, as opposed to having done an O of v plus e. So this is just O of v. All right. So let's just look at this, DFS versus union find and where, what has to be used. So if we look at DFS, so DFS is generally a very good traversal technique. It's, I mean, for all of our problems, we've mostly been using DFS, if not DFS. So it's for traversal, it's for exploring neighbors, paths and grids. And yeah, so it's like, what all can I actually reach? And now DSU is good for when you want to do grouping, connectivity, or merging components together. So it basically answers the question of, do these belong in the same group? So yeah, as you solve problems, you will understand like at what point you're going to have to use like a DSU union find, or when you're going to have to use like a DFS approach. So now let's go ahead and look at an example so that we can actually remember this. So yeah, right now I have a value of n is equal to 5. So n right here is the number of components that I have. And because everything is individual, I see that I have 5 nodes. I have 5 components. Now I have a mapping over here. So it's every node to its parent. So this is how union find works. We will look at the code in the next video where I actually take an example and solve it. So this, you might have to come to this for reference there. So what we store is every node and its parent. And initially, since none of the nodes are connected here, they are all the parents of themselves. It's like, I don't have any friends. I'm a group and I'm the leader of my own group. So that's what parent, ultimate parent here means. And their rank is 1. So basically, whatever in this case would be like the height of the tree that we were talking about. So that is where the rank comes. So everybody's rank is just 1 because it's just them. But as we go on, like combining them because of the edges they're connected with, these values will change. So let's see. So here I have an edge from 1 to 2. So once I connect 1 and 2, so the ultimate parent of 1 was 1 itself, and the ultimate parent of 2 was 2 itself, and they both had the same rank. So this is a case where I can actually union them together. And in this case, I'm going to assign 1 to be the parent of 2, and I'm going to change the rank of 1. We increase it by 1 when we have 2 components of the same height being combined together. That's when the rank increases because, as I mentioned, it's the height of the tree. So yeah, the parent of 2 will also be 1, and the rank of node 1 increases to 2. So after this, we have a connection 2 to 3, right? So right now what's going to happen, I'm going to go and check who is the ultimate parent of 2. And we see that that is 1. So ultimate parent, let's say I get 1. And who is the ultimate parent of 3? So the ultimate parent here is equal to 3, but there is a connected edge. So we're going to go and check which of these ultimate parents has a higher rank, right? And over here, we see that 1 is a parent that has a higher rank. So we're also going to attach, we're going to attach 3. So I'll draw this again, but they're going to get connected because of this edge over here. So yeah, the ultimate parent of 3 is also going to be equal to 1, and the rank remains the same. So now we go to 4, right? We have an edge connecting 4 to 5. So the ultimate parent of 4 is 4 itself. The ultimate parent of 5 is 5 itself, and they both have a rank of 1. So we need to combine them together, and both have the same rank. So either of them could be the ultimate parent, but let's pick the first one that first occurred. So let's make the ultimate parent of 5 will now become 4, and the rank of 4 is now equal to 2. And now we're going to have a connection which is 3 to 5, right? So what happens? 3's ultimate parent has now become 1, as we can see here. And 5's ultimate parent, let's probably rub this off. Okay, it's better. Yeah, so 3's ultimate parent is equal to 1, and 5's ultimate parent is equal to 4. Right. They're both different, but there's a connecting edge, and now we need to combine them together. And then I look at 1, and then I look at 4, and they both have the same rank. So what I'm going to do is I'm going to take 4, and I'm going to assign its ultimate parent to become 1 now. I just take the one that occurs first. So 4's ultimate parent will now become 1. And the rank, since the ranks were equal, the rank now increases because the height is increasing here. So 1's rank goes to 3, right? 3 to 5, yeah. And now we have another, which is 2 to 5, right? So what happens now? I call my union, and let's just rub this off here. So, yeah. So 2's ultimate parent is equal to 1, and 5's ultimate parent is it's still 4 right now. So we want to combine these together. So what's going to happen is because 1 has a greater size, it's obviously going to become the ultimate parent, and then the ultimate parent of 5 will also be equal to 1. And yeah, the rank remains the same. So yeah, we have 2 to 5 over here. And what this is actually going to look like is, I think it'll be something like 1 connects to 2, connects to 3, and then it'll connect to 4, which will be connected to 5, something like this, if I'm not wrong. Yeah, but they will all have the same ultimate parent eventually. So as we saw, each time where a successful union was happening, we were like, so we initially started with 5 nodes, but every time a union happened, it was like I was reducing the connected component size. Like instead of 5 nodes, like if I have 5 different nodes over here and I suddenly make a connection here, then from 5, it's going to be turning into 4, right? So I have 3 here and then I have 1 component here. So every time a union happens, we actually decrease that number because our individual component size is decreasing. So by the end of this, I actually remain with the size of 1. And that tells me that I only have 1 component. So this is the idea we're going to be using in a problem, which is like number of connected components in a graph or something like that, which we'll be solving next. So yeah, this is what happens. And so one more thing is, yeah, we only decrease it when we find a union, and that's why it's very important to return a true or false when union is possible. Let's say there are two nodes now that, let's say 3 and 5, right? So both of their ultimate parents are already 1. They're already 1, but let's say I called a union and I said I wanted to connect them. So it's very important to check if their ultimate parents are the same, because if they're the same, then we want to return that union returns a false. And that would help us here, because if it's returning false, then I don't want to decrement this component count, because if I keep on decreasing it for things that are already part of like the same group leader group, then I could be going negative, and I don't want to do that. So yeah, that's there. And there's also a way that this helps us in detecting like kind of like cycles, which is also another problem we're going to check. It's like, yeah, there will be another problem, but in a certain way, it does help us detect the cycle. It helps us detect an extra edge, something like that. So yeah, I hope you guys understood this. And yeah, this is, I really like this. So next we're gonna look at an example, like a problem. So you'll see the code, and I think things will make a lot more sense there. Like for the methodology and stuff, it's properly formatted, and you'll see the steps. So yeah, until then, happy coding, and I hope you guys understood this. So yeah, thank you.